Okay, now we have the other presenter is here, Deepak from NEC. He is going to be sharing, some of the activities, what the NEC is doing with the OpenPOWER.
Hi all, I'm from NEC, and we're going to talk about today about the hardware side to support your various applications for deep learning and machine learning. So what we have done on the hardware side is that we are coming up with a new technology to, it's an evolutionary technology for the next generation of data centers. So this involves basically hardware side, innovation. So I'm going to introduce today's PCI Express switch over Ethernet for distributed I/O systems. Now these systems can be used for ubiquitous computing and IoT application as well. So, and we are proud members of OpenPOWER, and our products which I'm going to introduce today is OpenPOWER Ready, and we seriously hope so to accelerate the applications, the data analytics, machine learning, and artificial intelligence applications through using our hardware. Okay. So what is the challenge we face? So our goal as a solution today is to provide real-time data analytics. So we have a lot of sensors, the Internet of Things, and it's uploading a lot of data to the cloud. And that's what we call that big data. And the data varies in 5 ways: variety, volume, etc. Now, in order to make sense out of this data, we need an actionable feedback, right? The data should be processed and analyzed in real time, and to get the valuable output as quickly as possible. And to do the same, the data centers these days are kind of clustering a lot of GPUs, a lot of I/O devices, as well as you're making big clusters of servers as well to solve this problem. But So the issue is that when we go for upscaling such data centers and hardware, we often find ourselves really worried about how we can scale out our hardware, which is required for our day-to-day software applications, for example, deep learning, right? And when we are preparing a cluster of GPUs and or FPGA accelerators, and even as from the storage side SSDs, we keep thinking about how to upscale. So NEC has come up with the solution to provide a dynamic deployment acceleration platform. And in doing so, what we're trying to do here is to have a kind of a system which extends the I/Os or GPUs or SSDs beyond the chassis of the computer. So what can be a dynamic accelerator deployment solution? So a technology in which we can extend the PCIe devices beyond the chassis of the computer. And what we are proposing here is that you can move out the GPUs or your SSDs out of the chassis of the computer. That means these GPUs or I/Os are remotely located outside your server. And in doing so, the advantage is that you can build up a system which is big enough and scalable enough, and you can do these resource sharing. So this is resource as a service. That means you can share your GPUs and SSDs cluster among different users. How we can do that is by extending the PCIe switch over Ethernet. Now, once we do that, what we do is that we provide Ethernet extension, and on the left we have a HBA card, which is located on the local PCI slots of the CPU, and on the right we have the I/O box, which is bare metal PCIe plugs, where you can plug in any of your GPUs or your SSDs. And segregating that is Ethernet. So Ethernet gives us two advantages. One is the length, and another is the switching capability. So regarding the length, it means that you can disaggregate your GPU cluster from your servers up till even 2 kilometers, and yet not lose on any efficiency. So the systems which we have tested with remote versus local, we are able to achieve 96% efficiency, and this allows us to have a kind of system which mimics the existing system. So on the left you see the existing system. So in the existing system we have a motherboard on which we have a CPU, the PCIe switch. The performance from the CPU side, this Ethernet should be invisible. That means the performance you get on the left hand side is the same performance you should get on the right hand side. That's the goal which we have achieved. And in doing so, we are able to realize something called as a broad scale single computer. That means on the left hand side is a traditional server or a CPU or desktop you see. On the right hand side is the next gen. So that means a CPU or sitting there can connect to any IO devices which is located across the campus. So it can be, your device can be like 2 kilometers away from your actual server, yet you can access that GPU or SSD, and you can share those IOs among the users as well. Now, what is the advantage? The main advantage is GPUs and SSDs make a lot of noise, and they are power consuming, and needs a separate room to cool down. So you can prepare GPU clusters on remotely in the campus, and you can still access them and share among the users. So in this way we can have a kind of a data center which is resource pooled, and we can upscale it as much as possible. And these PCIe lanes are reusable, and also we provide hot plug capability. That means you can plug out a GPU or SSD and plug it back in without disrupting the workloads which are currently going on the other servers. Now, how are we able to do that? We are able to do that by achieving a kind of something called a system on network. So system on network allows ExpEther to basically distribute the entire server system or your data center over the Ethernet, and this we are able to do by engaging the communication at the L2 layer of the Ethernet. So you do not need any new software stack. Everything which we have achieved through ExpEther, which is PCIe switch over Ethernet, is all in hardware. So as soon as you deploy this, it's a plug-and-play device, and you don't have to bother about installing any other new software stack for this purpose. So the picture in the slide exactly shows that. So on the left-hand side is the ExpEther software stack. On the right-hand side is the Ethernet stack. So there's exactly no difference. So it's a bare metal hardware you can install and start using. And think about the possibilities. You can build up on your own resource sharing system among the users, and also you can build and scale it up as much as possible, and resulting in starting from 1 GPU to a 16 to a 32 and a 48 GPU cluster. And you can keep on expanding the same. And overall, the idea is to achieve the system on network. Now, how are we able to do that? So we are able to do that by having these 4 unique features. So the first one is that we are able to provide these remotely located IOs to the CPU as local devices. Since there is no software stack involved, the CPU sees these remotely located GPUs or SSDs or any other PCIe device as local devices. So we are able to hide the latencies, we are able to manage the problems which Ethernet has, and we are able to provide the 96% efficiency of like local. So it is an equivalent to direct connection. And second is we are able to do that because it's very low latency. So first of all, we are working at the L2 layer of the Ethernet, and the Ethernet fabric has a lot of problems in the further slides I will be discussing, which we have dealt with, and made sure that this is a lossless connection and as per the PCIe specification, so that this Ethernet fabric always remain invisible. So that comes to the next point, is that we take care of, we get to the condition which is known as a no packet loss. So we are able to achieve that condition, that we have no packet loss, and we have an Ethernet system which is ExpEther system, which is running on Ethernet, and be robust. So this case is specifically about the dedicated network, which is meant for performance, and in this we are able to achieve a no packet loss and low latency condition because everything is in hardware. The fourth most important point which Ethernet provides is switching. Now, switching allows us to share our resources between different users. So let's just say we have a lot of users who want to get access to the GPUs, and on the time division basis, we can share the GPUs among the different users. And this is possible because we have an Ethernet switch involved, which can actually help us in reallocating these IO devices between the different users. So we provide IO dynamic reconfiguration and also hot plug. So for example, if one of the users plugs out one of the GPUs, rest of the jobs still keep on running. Now, how do we do that? So because Ethernet is very unreliable, and the bandwidth utilization is something which is a major concern in Ethernet. So in order to mitigate the same, on the top right is the ExpEther HBA, the adapter card which we install in the desktop. So on the input side we have the PCIe slot X8. On the output side we have the dual ports 40 gig Ethernet connections. So dual 40 gig means 40 plus 40, it's total 80 Gbps. So this is an X8 card which has the maximum throughput of 64 Gbps. We run this 64 Gbps connection over an 80 Gbps Ethernet fabric. So what's the point of having dual port is, first is it gives us load balancing for performance. So if there is a lot of traffic, we are able to load balance it by running the 64 Gbps over 80 Gbps. The second part is that Ethernet is unreliable. So if one of the switch in the network goes down, the packet can be rerouted through another switch. Now in this way we make sure that we have a lossless connection and the packet is delivered from the source to destination and with the redundant paths on the way. So because with PCIe specifications, as per PCI specifications, we do expect a lossless connection. So that's why this dual ports allows us not only throughput but also reliability as well. The next part is the usage of the Ethernet bandwidth. Now on the top you see is the typical TCP IP Reno, where in order to utilize the full bandwidth of Ethernet, it starts increasing the bandwidth initially, and whenever it appears to get collision, it lowers the bandwidth utilization. Now in this way there is a definite packet loss. But with the ExpEther on the bottom, you see we work with the probing mechanism. So the probing mechanism means that our management frames continuously go through every path on the Ethernet to check the time and latency of the packet delivery and the health of the connection. So in this way, we make sure that every path is fully utilized. So that means we utilize the 100% of the 80 Gbps bandwidth which is with us, and yet avoiding congestion. Multipath I/O also allows us to achieve various other applications. For example, you're looking for a failover recovery system. So if you have a failover recovery system using ExpEther, you can directly switch to the next I/O once one of the paths fail without actually shutting down your system. So within 2 servers, you don't have to shut down. You don't have to give time for recovery. You can automatically switch to the next I/O, which is the mirrored I/O, without losing your precious work. Now, another part is the dynamic reconfiguration and the hot plug capability. So on the left, this is which is the view of ExpEther. So on the top, you see there are 4 hosts. They're looking out for, on the bottom, these IOs to be accessed and through the Ethernet fabric. So these IOs can be reallocated or allocated to different hosts on the fly. And it can be done using ExpEther Manager software, which is sitting on the same network. And you can reallocate IOs, and this is what the logical view looks like. So for example, the group 1 is finished with IO, it can be allocated to group 4. And that can be done with the ExpEther Manager software. So ExpEther Manager software allows not only to basically group the IOs, but also to monitor the health of the Ethernet network. Now, up till now, I've been talking about PCIe basically is host to IO communication. But it's not only that. What you can achieve, this is the left hand side, but what you can also achieve is the interconnect. So, apart from the standard configuration, we have other configurations as well, in which the IOs can talk to each other without the involvement of the host through the Ethernet switch. So you can share your data. So for example, if you have a cluster of a GPU and an SSD together, so you can give the task to the GPU, and GPU can keep reading from the SSD and perform the task and give the result back to the CPU without its involvement. So that's peer-to-peer ExpEther. And then the next level comes in where multiple hosts can access the same SSD or the same GPU. So they can have an access, and we can have these accesses to, so we can achieve something called as the resource sharing. And going to the final stage is our LTBEE, where ExpEther, where the host can talk among themselves. So you see, not only host to IO communication, what we are allowing is all components to communicate to all, a kind of a system on network we are trying to achieve here. And this actually helps in some very critical scenarios where we feel that we need to scale out. First, we need to share data among users and make the data center highly efficient and low cost. So looking at the same, we provide different ExpEther equipment. So we have the slow version, which is the 1G 10G version. Now the 1G 10G version means 1 Gbps and 10 Gbps Ethernet. This is for the IoT side. So think about the possibility of connecting your sensors directly to your CPU without the involvement of a complex IoT stack, and it can be, your camera would remotely located would be looked upon to the CPU as a local device. And for doing so, we have the ExpEther 1G 10G version. For the performance side is the bottom one, which is the 40G ExpEther, in which we provide a box, and this box is capable of handling, we have a 2-slot and a 4-slot versions, and these boxes are capable of handling multiple GPUs, and such clusters of GPUs and SSDs can be made as a performing accelerator node and high performance storage nodes. So coming to our claims, so yes, definitely the performance. So this is the performance of ExpEther versus local. So what we see is that 96% of efficiency is achieved. So we installed the SSD in the local slot, we installed the SSD in the remotely located IO box, and we try to run the same operations of read and writes on the same, and we are able to achieve 96% to 100% efficiency. And these are, the distance is around 2 kilometers. So with the 2 kilometers difference, still we are able to achieve the similar performance, and that too for the read and writes. So yeah, and regarding the IOPS, so for the IOPS as well, so we are able to achieve the same IOPS in the SSD case, and we are able to achieve the same performance. And not only with SSDs, but we also come up with the NVIDIA GPGPU. So this is the figure of the GPGPU P100 N-body test. And you see the local configuration. So we installed a GPU in local slot and remotely. You see that the lines are completely overlapping here. So we give, here we have achieved around 99 to 100% efficiency. So our remote versus local efficiency is same. And this is very motivating in the fact that that means the GPU, which is a kilometer apart, is giving the same performance as the local one. And looking at such a performance and such data, we can actually realize such a system. So on the top right, you see is an accelerator node where you can have a cluster of GPUs or accelerator FPGAs. And on the bottom, you can have a high speed storage node. So we have an example of ADS 1000, which is a 24 SSD to URAC, and it's connected through Ethernet switch, and it can be accessible to the compute nodes. So you can have accelerator nodes, compute nodes. So this is the accelerator resource pool system. On the bottom you see is more of the IoT side, where you can attach your sensors directly to your CPU. And these are all Ethernet based. And deployment of Ethernet is the most easiest. So most of the IoT sensors and IoT data is IP network based. So deployment of this system would be very easier in IoT cases as well. So we did some deployments. So this is the case with Osaka University, where we deployed 64 servers and 70 IO devices. And you see here is the bottom is the stack. So there were multiple servers, and we have ExpEther Manager software, which is reallocating this GPUs and flash drives, as well as the hard disk, to the servers on the fly. And we were able to achieve the same as local performance, and this was really helpful in specifically in cases of VR, virtual reality, and also in case of image and video analytics. Looking at the IoT side, so we were able to connect to different sensors in the medical equipment domain as well, the PCI extensions, and we were able to deploy our systems in the medical imaging domain. So for example, you are sitting close to the MRI scan, so a doctor can be remotely located and operate the MRI scan machine from remote location, and yet not losing on the performance. And coming on to the failover recovery. So this is the use case which we developed using Express Cluster software of NEC along with ExpEther. So Express Cluster software is a high availability system, and it provides the efficiency of 5 nines. And that means it's a 5 minutes downtime in a whole year. Now, replicating such a system using ExpEther was a challenge, but yet we were able to achieve it. So that means these SSDs you see on the bottom were, the systems were easily able to fail over using PCIe devices. So that means you don't have to switch off your server, or you can easily, smoothly fail over, and we were able to do it in the order of microseconds. And we were able to fail over from the system to the backup server. Now looking at the possibilities. So we at NEC see the IoT cloud, IoT layers as 5-layer system. And on the L1 side, we can have the smart devices using the 1G, 10G, which is a low power version of ExpEther, and we can deploy it for the IoT scenario. Even at the edge side, we can have such low power systems. Coming onto the data center side on the top, the cloud analytics stage, we can basically deploy the high performance ExpEther version. And in future, we are coming, this is the hardware ExpEther. In future, we are coming up with the Wi-Fi version of the ExpEther, and also the software version of the ExpEther. So that means you will be able to connect your devices through Wi-Fi as well as through the software version. So what does that mean? It means that the cell phone you see on the top left can connect to your GPUs for deploying data and performance, and get back the processed data. And similarly, if you have a car infotainment system, and if you need to sync up with your systems at home, you can do that. So what does that mean? It means it's a single unified protocol, combining 2 legacy protocols together to achieve something which is barely simple, and yet giving you the performance value needed. So, so with ExpEther, yes, we can achieve the same, and we can achieve a kind of a universal interconnect, and learning from the 2 legacies. So in summary, ExpEther is a resource disaggregated system, and the distance allows you distance or length with dynamic switching capability you get, or you get the same performance as local, and moving the devices within the chassis is now easier. So you don't have to shut down your PC just to plug out your card, right? And making legacy useful in a most cost-effective way. So PCI is a very, PCI and Ethernet are very long time tested protocols, and there are a lot of devices already supported on these. And so with the resource disaggregated system, we can very well achieve the next generation scalable data centers and also the IoT domain, and we can address the problem of the hardware support needed for the latest applications with the software guys are coming up, for example, deep learning. So we have a consortium with us as well, ExpEther.org, to come up and with your ideas and share with us. So with this, we wish to propose a new interconnect system for the next generation data centers and solving the problems of the machine learning and AI from the hardware side. So I thank you all for listening, and I hope you find it useful enough to think about it and discuss with us. So our booth is at second floor.
Okay, let's give a round of applause to Deepak.
Thank you.
Thank you, Deepak.